In the last video, I proved that if you've got a dense bipartite graph with, well, it has to have two finite vertex sets in order to make sense of the notion of density. So if you have a dense bipartite graph, then you can find a pretty large subset of one of the two vertex sets, such that almost any two vertices in that subset will be joined by many paths of length 2 in the graph. And as I said at the end of last time, what we're going to do this time is a result where we can get from almost all to all, but the price we pay is that instead of paths of length 2, we have to go for paths of length 3. So let me just remind you what we did, what the statement was last time, slightly more precisely. So here it is. We had a lemma. If we've got a graph of density delta, bipartite graph with vertex sets x and y, then for any constant c, you can find a subset. When I say it's reasonably dense, this is an estimate for its density, at least delta x divided by the square root of 2. And the number of pairs that fail to have a lot of paths. So that this, if you recall, was the co-degree of x1 and x2, which is the same as the number of common neighbours of x1 and x2, which is the same as the number of paths of length 2 from x1 to x2. The number of pairs such that that's less than c times y, so such that you do not get quite a lot of paths of length 2, is at most this thing here. So as long as we choose c to be reasonably small so that it cancels out the fact that delta to the minus 2 could be quite large, so as long as c is substantially smaller than delta squared, then we get a non-trivial statement here. We get that a fraction at least 1 minus 2c delta to the minus 2 of the pairs in x dashed squared, where x dashed is this subset we've just chosen, are joined by lots of paths. So now let's, what we're going to do is, as I say, a similar thing for paths of length 3, but of course because it's a bipartite graph, that means we'll have one subset of x and the other subset will be a subset of y. And the idea is that for every x in x dashed and every y in y dashed, we have lots of paths of length 3 from x to y. But before I do that, I want to prove a lemma of a kind that is sort of ugly but necessary sometimes. So when I say necessary, I think I'm not sure I know of an example where it's really 100% necessary, but it's just convenient. So here we go. Lemma. Oops, done too many squiggles there. Start again. Lemma. Let a1 up to an be some numbers between 0 and 1, inclusive. If the sum is greater than or equal to an, then the number of I, so this is the same as saying that the average is greater than or equal to a, so the number of I such that ai is greater than or equal to b is at least a minus, am I going to get this right? Yes, a minus b over 1 minus b times n. If I've got that bound, if I've misremembered it, well, we'll get the right bound very soon in the proof, but I think that is right. I'm going to do a quick sanity check. We need b to be smaller than a in order to have any chance of proving anything, so that at least is the right way around, and I think that makes sense. So proof. Let G stands for good, not graph or anything like that. So G be the set of I such that AI is indeed greater than or equal to B. Then we get that AN is less than or equal to by hypothesis, the sum of the AIs, which equals the sum over all I in G of AI plus the sum of all I not in G. It's a very common step to do, by the way. You've got a sum and you just split up into ones that satisfy some bound and ones that do not satisfy some bound. Now let's bound those two. So what can we say about AI if it belongs to G? Well, as far as an upper bound is concerned, we can't say anything very much except that it belongs to 0, 1. So we certainly get that it's at most the size of G. And here, the number of things we've got is n minus the size of G. And each one is less than B. I'll be sloppy about the less than. I don't really care that it's strictly less than, so we can just put B. And now let's rearrange. That tells us that G is greater than or equal to, let's subtract Bn first of all, so we get A minus B n, and what's left? We've got G times 1 minus B, so we divide that by 1 minus B, which is exactly what I claimed. Now there are a couple of regimes where we use this lemma, and I could have proved them separately. In some ways it would be more natural to prove the two things separately, but since they had essentially the same proof, I thought I might as well unify them. So one of them is the case where, so we're going to use them in the following two cases. One case will be, so e.g. So one case will be where A is small, or smallish. So if B equals A over 2, and A is reasonably small, then the size of G is greater than or equal to, that's at most 1, so we can get it's at least AN over 2. So what can we conclude from that? That's saying that if the average is A, then you're at least A over 2, at least a proportion A over 2 of the time. But another example is if A is close to 1, in which case it's natural to write A as 1 minus theta, and B equals 1 minus eta, let's say, then then G in that case, this A minus beta, A minus B, I mean, is eta minus theta, and 1 minus B is just eta, make it times n, which equals 1 minus theta over eta times n. So if eta is somewhat bigger than theta, this is reasonably small, and we're going to apply this again. We'll apply it in the case if eta equals 2 theta. This tells us that AI is greater than or equal to 1 minus 2 theta at least half the time, or at least for at least half the values of I, because then 1 minus theta over eta will be at least a half. Okay, so these are just, I always feel it's a little bit of a failure ever to use this lemma, but I'm going to use it a couple of times in what follows. So let's go ahead and prove the main result of this video, which I'll still call a lemma. Let X be a bipartite graph. Sorry, G I mean. So forget that I used the letter G up here because it means something completely different now. G be a bipartite graph, and I really can't afford to use anything else because I need another graph later on. So let G be a bipartite graph with density, well, so with vertex sets which are finite, X and Y, and density delta. then there are subsets x dashed of x and y dashed of y such that now the numbers here come out sort of slightly differently every time I prove it, and that's a slight exaggeration, but nevertheless, just to emphasize that you write down the proof and then you see what the numbers are. And the idea that what matters is the ideas of the proof. So I'm not going to, I've sort of not in fact memorized them before giving you this video. I just know that they're going to come out reasonable. So I'll just say x dashed is greater than or equal to some fraction of the size of x, which will depend in a reasonably nice way on delta. Y dashed is going to be at least some fraction of y, and every x in x dashed and y in y dashed are joined by at least a certain number, some constant, times the maximum possible number, which is the size of x times the size of y, paths of length 3 in G. So why this size of x times the size of y? It's because to get from x to y by a path of length 3, you first of all have to choose some vertex in capital Y, then you have to choose a vertex in capital X, and then you have to go to Y. So the absolute maximum possible would be if you could choose any vertex you like in Y and any vertex you like in X, and then you could go from X to that vertex to Y. By the way, path of length 3, I allow it to go back and revisit X. I count that still as a path of length 3, even if it's a degenerate path. And so, as I say, I'll fill in all these constants when we get to the end of the proof, but the key point is that they are reasonably nice numbers. They'll depend in a power type way on delta. And I can tell you in advance that if it comes out the same as when I last did it, it should be delta to the 6 divided by some biggish power of 2 as my constant. In fact, I think it'll be delta to the 6 over 1024. But let's go ahead and prove the result. So it's going to be extremely convenient for this if so here we've got the density delta is telling us what the average degree of a vertex in X is. It'll be delta times the size of Y. But I'm going to be passing to subsets, and if you pass to a subset of X and all you know about is the average degree, then when you pass to the subset, you don't know whether you've got any edges at all. So to avoid that kind of problem, I don't know why I've written the word prove here rather than proof. I think maybe I said the word proof. Said the word prove, I mean, as I wrote it. I seem to have trouble saying one word and writing another. Okay, so back to here. What we're going to do is pass to a subset of X so that the minimum degree rather than just the average degree is large, because if you've got a subset where the minimum degree is large, then whenever you pass to a further subset, you still have large minimum degree. So by the previous lemma, X has a subset X1 such that every vertex in X1 has degree at least delta times the size of Y over 2. That's trivial, it could be empty, but now I'm going to say and the size of X1 is at least delta times the size of X over 2. So just to see why that follows from the previous lemma, in case that's not instantly clear, the normalized degree, if you remember, that's the degree, the normalized degree of a vertex in X is the degree divided by Y. So the normalized degree lies between 0 and 1. The average normalized degree is delta. So if you just look at, if you let n be the size of X and A1 up to AN be the degrees of the various vertices in X, then from this lemma, and in particular from this first case of the lemma, we have that the average normalized degree is delta, so it means that we can find at least delta n over 2, or delta to the size of X over 2 vertices where the normalized degree is at least delta over 2, and that's exactly the same as saying that we can find a set of size at least delta x over 2 such that the minimum degree is at least delta y over 2. Or you just, don't even really, if you don't want to, don't use the lemma, you just prove this special case. Of course, the fact that I had the numbers lying between 0 and 1 wasn't important. It could, just as long as it lies between 0 and some bound, and that the average should be some reasonable proportion of that bound, is what matters. It's because it scales up and down in a nice way. Anyway, so we've got the minimum degree at the cost of dropping down to a subset of size delta over 2 times the size of X instead. So now let's apply the lemma about paths of length 2. So by the 2 paths, paths of length 2 lemma, for any C, x1 has a subset x2 of size at least delta times the size of x1. Oh, wait a minute. I have forgotten a remark, which is that I'll insert it in here. So the density of the graph induced by x1 and y, so that's if I just restrict the vertex, I restrict x to x1, so I just look at the parts of the graph where one vertex is in x1 and the other vertex is in y. So the density of that, because the minimum degree is delta over 2, it's at least delta over 2. So I've had to drop the density by a factor 2, and I've had to drop the size of x by a factor delta over 2, which is a little bit more expensive, but the gain is I've got this minimum degree bound. So by the 2 paths lemma, so what size do I get? Let's just go back and have a look at the lemma. So the size was delta x over 2, except that now delta has been replaced by delta over 2, and x has been replaced by x1. So back down here, so it's over root 2, I mean, so it's delta times the size of x1 over 2 root 2. So it's delta over 2 is the new delta, and then the root 2 is the root 2 that we had before, such that for all but at most, so it's 2c delta to the minus 2, but that's the old delta. The new delta is half of the old delta, so I have to multiply by a further factor 4. So 8c delta to the minus 2 x1 squared pairs x1, x2 in x1 squared. We have that the number of paths from x1 to x2 is greater than or equal to c times y. And we will choose c later on. In fact, we'll choose it pretty soon. So x2 is going to be, oh wait a minute, next thing I want to say So we're going to define a new graph. Let gamma be a graph with vertex set. So gamma is sort of standing for good here. So vertex set x2 with x1, x2 and edge, if and only if the number of paths from x1 to x2 is at least c times the size of y. So this statement here says then the average degree of gamma is, by the way, strictly speaking, this is a graph with loops. In other words, a vertex is allowed to be joined to itself. And when I talk about, so if x1 equals x2, that's just the number of neighbors of x1. Anyway, the average degree of gamma is at least 1 minus 8c delta to the minus 2 x1, because the total number of edges is going to be the average degree times the size of x1. Oh, the total number of pairs, I mean. These are... perhaps I should call it a directed graph or something like that. No, actually, I'll just call it a graph, but the average, the number of pairs is, the proportion of pairs is at least 1 minus 8c delta to the minus 2 times this squared, and so that is telling us precisely that the average degree is at least this number here. So, by the previous lemma, the sort of ugly averaging argument lemma, and the second thing where I had a theta, so now my theta is going to be 8c delta to the minus 2. So by the previous lemma and the second case, at least half the vertices in x2 have degree at least 1 minus 16c delta to the minus 2 times, that should have been an x2 there, because the vertex set was x2. And then, sorry, that should also be an x2, and that should be an x2. So I've passed from x1 to x2. It's a slight disadvantage of doing these online, that kind of thing gets picked up a bit more slowly, if at all. I apologise for that if that confused you a little bit. But we'd passed to this subset x2, and we've been living inside x2 for all this time. So let x3 be the set of all such vertices. So all vertices that have degree at least this in gamma. And just while we're at it, let's see what size, and then we'll set x dashed to be x3. So let's see what size x dashed is. So x dashed is greater than or equal to a half x2. x2 had size at least delta x1 over 2 root 2. So that's greater than or equal to delta x1 over 4 root 2. And what was x1? x1 had size at least delta x over 2. So that's greater than or equal to delta squared x over 8 root 2. And so now we can go back and fill in delta squared over 8 root 2 times the size of x. Now, every vertex in x dashed has degree at least delta times the size of y over 2. So the graph induced by x dashed and y has density at least delta over 2. So at least so that means the average degree of a vertex in y inside x dashed. Perhaps I better write that as a separate step actually. I was going to jump a step, but so the average degree of y in x dashed, where y is chosen randomly from capital Y, is at least at least delta times the size of x dashed over 2. So at least delta y over 4 vertices in y have, again by this averaging lemma, have degree at least delta times the size of x dashed over 4. So let y dashed be the set of all such vertices. So y had size at least delta y over 4, so up we go and put that in, delta over 4 times y. There's a slightly unpleasing lack of symmetry here, but that doesn't matter too much. Now we want to show that every vertex in x dashed is joined to every vertex in y dashed by lots of paths. And before we do that, we're going to have to choose what C should be. So let x belong to x dashed and y belong to y dashed. Then x has at least 1 minus, so remember x has degree at least 1 minus 16c delta to the minus 2. So 1 minus 16c delta to the minus 2 times x dashed, times x2 neighbours in x2. I've made another annoying mistake. All these x dashes should have been x2s. So every vertex in x2 has degree at least that. So the graph G induced by x2 and y. So the average degree of y in x2 is at least delta times the size of x2. Everything I wrote actually was correct, but it's not what I need now. So the fact that it was correct means that the argument just carries through in exactly the same way. But here I do want to say let x belong to x dashed. So x has at least that number of neighbours in x2 in the graph gamma, and y has at least delta x2 over 4 neighbours in the graph G. So there are at least delta over 4 minus 16c delta to the minus 2 x2 neighbours in common. And so what we're going to do is just choose C so that this thing equals delta over 8. So let C equal delta cubed over, it looks as though it's got to be delta cubed over 4, over 8 times 16. And what's 8 times 16? It's 128 because it's 8 eighths times another 2. So let's C equal delta cubed over 128. Then there are at least delta size of x2 over 8 neighbours in common. So remember, these are neighbours in slightly different graphs, but we can use this now to work out how many paths there are, or if we get a lower bound for the number of paths. So the number of paths, and it would be a little bit ugly, of length 3 from x to y is at least, well, what I'm going to do is I'm going to come from y to one of these common neighbours, and I can do that in at least delta x2 over 8 ways. And now I want to go to get from that neighbour of y to x by a path of length 2, which will then make up a path of length 3. So how many ways can I get to x? Well, gamma, that graph gamma, where have I defined it? I define it to be to have an edge if the codegree of x1 and x2 is at least c times the size of y. So that means that the number of paths from any neighbour of, or any common neighbour, or but anyway from any neighbourhood, so any neighbour of x to x of length 2, any neighbour in gamma to x is going to be at least c times y. And now let's just say a little bit about what that is. So we've got a delta over 8, and a c was delta cubed over 128. And what was x2? X dashed was at least half of x2, and just to remind myself quickly, and x dashed was at least delta squared over 8 root 2. So we get delta squared over 4 root 2. We can have it here. And we had a, so then times x times the size of y. So what does this end up as? Well, that gives us a delta to the 6. But less than or equal to, so this root 2, there's no point in keeping it when you've got such a big power of 2 anyway. So 128 is 2 to the 7, that's 2 to the 3, so we've got 2 to the 10 times another 2 squared, so that's up to 4096 times root 2, so we've got 2 to the 12, let's say delta to the 6 over 2 to the 13. That's not quite as good as I thought it was going to be, but it's okay. And I shouldn't have said less than or equal to because I wanted a lower bound, but it is greater than or equal to. So let's put that in, delta to the 6 over 2 to the 13. Now, as I said before, the main point is that, what I suggested, that this number here is just a smallish power of delta divided by some constant. This is also, what's it, even just linear in delta. And this is, again, a not too large power of delta divided by not, well, it's slightly irritatingly large, but it doesn't really matter. So, in qualitative terms, we've got exactly what we want. So we've got a fairly large set x dashed, a fairly large set y dashed, every x in x dashed and every y in y dashed are joined by a large number of paths of length 3. And just to sort of recap slightly, the idea was that perhaps I'll draw a picture of what we've just done, just to finish off the video. So we started with x here and y up here, and then we passed to a subset x dash. I'll draw it reasonably big, but in reality it could be a bit smaller than that. Well, we passed to x2. I'm going to sort of jump 2 steps. So x1 we passed to so that we made not just the average degree reasonably large, but the minimum degree reasonably large. And then we passed to x2, where almost any 2 vertices are joined by several paths of length 2. So a sort of typical pair of vertices down here will be joined by many paths of length 2. Now what that implies by a sort of averaging argument is that for a typical vertex, there will be almost all the other vertices will be joined to that one by lots of paths of length 2. So just to sort of, what's the general principle here? If almost every pair has some property, in this case being joined by lots of paths of length 2, it is the case that for almost every vertex, almost every other vertex forms one of these good pairs. So what we then do is we sort of lop off a little bit of x2. In fact, the way I've did it, I lopped off half of x2, so that then everything in this half is joined to almost everything else in x2. Now I restrict to vertices in y that have large degree inside x2. Now if I've got a vertex y, and I've got a typical vertex here, x, y has large degree over here, or sort of not tiny degree. And because x is joined to almost all other vertices by lots of paths, and in particular it's joined to at least half of these ones by lots of paths, but y is joined to all of these ones, so we've got lots of paths because we can go to anything in this set here, and then whatever we end up in this set here, it will be joined by lots of paths to x. And that gives us our large collection of paths of length 3. And with that much less formal explanation, I will finish this video. Thank you.